Mr. Harry, Mr. Ryan, alright? Okay, so yesterday we talked about the k-smallest binary search tree. Okay, so binary search tree, the node, it's binary tree where the left nodes are smaller than the root and the right nodes are bigger. For example, like 4, 5, 6. Okay. So how do we traverse the binary search tree in order to get the sorted list?
4, 5, 6.
Yeah. What order is
In
that?
order.
In order. Okay. So yesterday.
That was smart.
Yeah. So yesterday we talked about this k-smallest binary search tree. Yeah. So we're using this in order traversal in order to get sorted list, and then we talk about the yield. Yeah. We talk about the iterator yield thing. Yeah. Because look, the k could be very small, the total number could be very big, and in order to get the k-smallest node, we don't need to actually visit all the nodes. Yeah. If just imagine that t could be a million, more than a million. Yeah. It could be very large, right? So. Yeah, so we talk about this recursive in order thing. Okay, so today we're going to solve this problem, using another approach. So let's say, okay, so just imagine, imagine this is a binary search tree. Yeah, I have a node. That's the root node, and I have a left tree. Yeah, obviously I have a left tree, but I don't know how many are there. Yeah, I don't know how many are there. I have the right tree here. And again, I don't know how many of them. Okay, look, listen. If I'm telling you that, there are k minus 1 node here. So which node is the k-smallest node? Come on. If there are k minus 1 nodes on the left of root, exactly. Why is that? Because the nodes on the left tree are smaller than the root, right? Yeah. So if I'm saying k minus nodes are on the left tree, so it makes the root a k-smallest, right? Make sense? Okay, so now if I'm telling you there are more than k minus 1 nodes on the left, what happened? So look, this is, let's say there are n nodes, okay? If n equal k minus 1, then the root is the k-smallest one, right? Root, this is the k-smallest one, alright? But if I'm saying that there are bigger or more than k nodes, what happened? If there are many nodes, more than k nodes on the left, so where is the k node going to be? Where is the k node going to be? If there are if n is more than k, if there are more than k nodes on the left tree, so where is the k node going to be? Come on, it's exactly. You'll be on the root of left, yeah, somewhere on the root of left. But we have to recursively find it out, right? Okay. How about n smaller than k? This is the tricky part, right? Look. This is the tricky part. If there are n nodes, if there are less than k nodes on the left, there are k. Come on, Eric, on the right, yeah. But it's on the right. But if we keep finding on the right, so look, Eric, look. This is the tricky part, okay? So look, root on right. It's on the right. So look, there are 1 node. This 1 node, the root. There are n nodes on the left, right? So k is bigger than n. So k minus 1 minus n. There will be the node on the right, right? So what does it mean? Look. If k is bigger than n, right? And we are finding the k-smallest node, right? But it's on the right tree, right? Yeah. Am I right? On the right tree. So look, I have to minus 1 node because I know there's 1 node smaller than the k, and there are n nodes here, right? There are n nodes here. So the nodes should be k minus 1 minus n regarding root of right. Does it make sense, Eric? Okay, let me repeat this again. Okay, come on, Eric, Ryan. This is interesting. I'm finding n nodes on the root of left. Root of left has n nodes. Okay? If n equals k minus 1, great. That makes the root the k-smallest. Do you understand this part? Okay, if n is more than k or equal than k, if there are more than k or equal than k nodes on the root of left tree, so where is the node going to be? Where is the k-smallest node going to be?
Left.
Yeah, it will be somewhere here. And then we can recursive call it. Recursive call it.
Here.
Yeah, but the second parameter is which node? You will be still on case node, eh? The case node will be still on the left tree, right? Yeah? Okay, now the tricky part is on the right, right? So if the k no, if k is bigger than n, if n is smaller than k is bigger than n, right? So obvious is on the right tree. But which node? I mean, what's this case node going to be? Which node on the right tree? We have to subtract one node here and node there, right? Make sense? Does it make sense? Okay. Look, if there are 5 nodes here, 1 node here, and then if we want to find the 10th node, right? If we are going to find the 10th k equals 10, and there are 5 nodes here, 1 node here, right? So the root of right tree, the node would be 10 minus 1 minus 5, right? Yeah, because we already found 5 plus 1 nodes which are smaller, which is not the node we are looking for, right? Alright. So using this, we can just do this recursion. Yeah, we can just do this recursion. And then first of all, we need to have this count function to count the number of nodes in the subtree. So we can do it many ways. Can you give me an example? How do we find the number of nodes in the given binary tree? We talk about this. Yeah, we can use what kind of search? Depth search, breadth search, exactly. Okay, let's do this depth search. Yeah, define depth search root. If not root, return 0. Otherwise, return depth search root of left plus 1 plus depth search root of right. We can even using the lambda function. And lambda dfs equals lambda root and dfs root of left plus df plus 1 plus dfs root of right. If root, yeah, okay. This is the depth search. And how about the breadth search? Breadth search is also very easy to implement. What kind of data structure we need to use in order to do the breadth search? DQ, yeah. If not root, return 0. Otherwise, we have a DQ, root of left. And then while Q, I have to put it in n equals 0. N plus 1, we have one more node, yeah? A equals Q dot pop left. If A dot left, we push it back to the Q dot append, A dot left. If A dot right, Q dot append A dot right, yeah? And then we return the n, right? Return the n. This is the breadth search. Okay, and then coming back to the recursion function to find the case models, okay? Define case, okay, root. N equals, let's use the depth search root dot left. We're counting the root left tree, okay? Now look, here, okay, the second parameter. If n equal k minus 1, return what? If n equals k minus 1, return what? There's no answer, return what? If n equals root, yeah. Okay, wait that. Okay. If n is bigger than or equal k, return what? It's on the left tree, right? So case, calling the recursion, yeah. Root dot left. And then the second pin was still k. Okay. And otherwise return case. What should I do with the list? If it's now where is the root? Where is the case node going to be? Case bigger than k, on the left tree. Otherwise, it's on a right tree. Root of right. And which node is it? That value we talked about. Which node is it? K minus 1 minus n, right? Yeah. And that will be the recursion. Yeah. Yeah. What have you learned today? What's the time complexity for this one? The in order. The method time complexity is all n, right? If we're going to visit all the n nodes, yeah. But if we're using the iterator, yeah, we stop searching. If we stop searching after finding the kth node, then the time complexity is okay. Sometimes you pass the height h, okay, because that's going to be the height, yeah, the height of the tree. For this method, yeah, the worst case scenario. Okay, if you don't understand the time complexity of this one, let's look at these very extreme cases. Look, 1, 2. Look at this, 3, 4. Here, K. Okay, I'm going to find out the K smallest node. Which node is it? Which node is it? That's the first smallest node. Which one is the K smallest node? Yeah. So for each one, I'm going to call this recursion. Yeah. But look at each call, there will be a depth first call. So the time complexity will be O n times n. This is O n, right? And then O n times K. Okay, K smallest. Okay, K smallest. Make sense? Yeah, so the time complexity will be O n times K. And in the worst cases, right, look, because K is smaller or equal than n, so it makes O n squared, okay? Make sense?
Yeah.
Okay, that's it for today. Bye bye.
Bye.
Bye bye. Bye bye.